In this lesson, we're going to talk about scatter plots and determining the line of best fit for our data. And we've got a couple of vocabulary terms on this first slide. First thing is talking about the line of best fit, or in this case it'll be the line, but in other cases it might be a curve. But it's basically just your line that lies as close as possible to all or as many of the data points as possible. Regression is just the method that we use to find the equation of the line of best fit, and today we're going to talk about doing this by hand, and then in class we'll talk about doing it using our calculator. And one of the reasons that we even determine what our line of best fit is in order to make predictions based on our data. So data is gathered over a certain period of time or for a certain number of people or whatever it might be, and then we make predictions based on that data. So if we make a prediction based on a value that is outside of the domain, then we call that extrapolation. And I remember extra beyond the being beyond the data set, or beyond the domain of the data set. And then interpolation is if we make a prediction and we use a prediction using the values that are within the domain. So we'll talk about those in context in a minute, but those are some vocabulary terms that you need to become familiar with. Let's look at this first example. I apologize, it takes me a while to plot these points. It's a little difficult to do using a slate. But let's go ahead. We've got 18 and 8. Well, first of all, let's label our axes. But we've got the number of cans sold and those recycled. So we've got the environmental club looking at the relationship between the number of canned beverages that are sold and the number that are recycled in the cafeteria. So when 18 cans were sold, 8 were recycled. When 15 cans were sold, 6 were recycled. When 19 cans were sold, 10 were recycled. 8 and 6, 10 and 3, 13 and 7, 9 and 5, and 14 and 4. Alright, so we've created our scatter plot, and now we're going to use our straight edge to determine the line of best fit. If you have a clear ruler, that's really helpful for this. So I've got my line. There's one. Maybe draw another one. A little bit below. I don't really like either of those. Let's see. Let's try this again. That's a little bit better. Okay, so we'll go ahead and go with that one. And we're going to, once we've determined or using our ruler where our line of best fit should be, we're going to use 2 of the points in my data set to find the equation of the line. So this one clearly falls on my line, and then this one is probably the next closest to it, so those are the 2 I'll use. So 18.6 and 15.6, or excuse me, 18.8 and 15.6. So if you recall from the review video on writing linear equations given 2 points, this should be pretty easy. So we've got our slope is our change in y over our change in x. So I've got 8 minus 6 in the numerator, 18 minus 15 in the denominator, and so that becomes 2 over 3. So I've got a slope of 2/3, and then I'm going to choose one of the points to go ahead and plug in. So y minus, not equals, y minus y1 equals my slope times x minus x1, which is 18. And then remember I'm distributing here. Y minus 8 equals 2/3 x minus, and on the top I end up with, in my numerator, 18 times 2, so 36, and 3 in the denominator. So I'm going to go up here and simplify that. Y minus 8 equals 2/3 x plus 12. And then I'm going to add 8 to both sides to get it into slope-intercept form. So y equals 2/3 x plus 20 is my equation. Alright, and looking back, I just caught my mistake, and I hope you did too. This should not be plus 12, that should be minus 12. I knew something wasn't right. So let's go back. Then when I add 8, it's minus 4, which makes more sense for my y-intercept to be negative 4. Alright, so there's my equation. Y equals 2/3 x minus 4. Now, if you drew a different line of best fit and used different points, different coordinates, then your equation is going to be slightly different than mine. And then let's talk about the domain and range. Remember, domain is all possible x values, and the range is all possible y values. So when I look at this equation, or excuse me, not equation, yes, this equation, but mainly at this table and this scatter plot, one thing to note is that this is a discrete function. So I've got these individual points that make up my scatter plot, and to connect them wouldn't make sense because it's not continuous. I don't have a continuous, as far as my cans that are sold, it wouldn't make sense to connect between 14 and 15 because I can't sell 14 1/4 cans or 14 1/2 cans. So these are discrete values, which means that my domain and my range are also just going to be a list of discrete values. So when we do that, we put them in braces. So for my domain, all my x values, and I'm going to go ahead and list them in order. So we've got 8, 9, 10, 13, 14, 15, 18, and 19. And then for my range, notice it's this list of values, but 6 is repeated, so I only have to list that once. So I've got 3, 4, 5, 6, 7, 8, and 10. So those are my domain and range. The second example is talking about Mike riding his bike home from his grandmother's house. So we've got X representing the number of hours that he's been riding his bike, and Y is the representing the number of miles he is away from home. So let's go ahead and make a scatter plot below. So we've got, after 1 hour, he is 35 miles from home. After 2 hours, he is 29 miles from home. After 3, he's 26 hours from home. 4, he's 20 hours from home. 5, he's 16. 6, he's 9. 7, he's 6 miles from home. And 8, he's 0 miles from home. Alright, describe the association between the data points on the scatter plot. So we've got, again, the hours that he has been riding his bike, and then this is his distance from home. Now remember, this is distance from home, so notice as he gets closer to home, he is his y values are getting smaller. So the association between the data points on the scatter plot, you can look and see how far he went in 1 hour. He went from 35 down to 29. So let's go ahead and use our straight edge to approximate our line of best fit. Let's try this. Alright. See if I can get that. I don't think it's going to move. Alright, we'll just use it as it is. Alright, and then we have to find our equation. So we're going to choose 2 points on our line. So it looks like this one, and I'll go ahead and just use this one. So we've got 326 and 6, 9. So first thing, to find my equation, I need my slope. So I've got change in y, so 26 minus 9, over change in x, which is 3 minus 6. 26 minus 9 is going to be 17 over negative 3. So think about it. Does it make sense that I have a negative slope? Well, look, my line right here is showing a negative slope, so yes, it does. Alright, and then I'm going to choose a point to use, let's just use 6 and 9 for the sake of having smaller numbers. But I've got y minus y1, so 9 equals slope times x minus x1. Alright, and I'm distributing, so I end up with y minus 9 equals negative 17 over 3x plus, because when I multiply two negatives they become positive, and on the top I've got 17 times 6, and on the bottom I've just got 3 times 1. So I'm going to go ahead and simplify 3 into 6 goes twice, so 17 times 2 is 34 over 1. Now you could easily have multiplied 17 times 6 and then divided by 3, and you will end up with the same answer. So lastly, I'm going to add 9 to both sides, so y equals negative 17 over 3x plus, and when I add 9, that's going to become 43. So when I look at my equation and compare it to my graph, I've got a negative slope, 17 over 3, so roughly negative 6, so down 6 over 1, that looks about right. And then a y-intercept of 43, which means it would be crossing up here, which seems quite appropriate to be up here right around 43. Alright, what does the slope represent in the context of the problem? So right here, my slope, remember that would be his rate of change. So in this case, my slope is miles per hour. So how far he's going after 1 hour, how much closer he is to home after 1 hour. And then the y-intercept represents in the context of the problem would be how far he was originally, so basically how far Grandma's house is from his house. And then it asks, could you use your equation to predict how far Mike would be after 10 hours? Use mathematics to justify your answer. So if I were to use my equation and plug in 10 hours, remember time is my x value, so I could just plug in negative 17 over 3, plug in 10 for x, and then plus 43. So I end up with y equals negative 170 over 3 plus 43. So when I add those two together, negative 170 divided by 3 is going to give me approximately, and I'm just using approximation here, negative 56.7. So when I look at that, it's going to give me a negative answer. Okay, so my negative answer ends up, in the context of this problem, not making sense. And if you look at your graph, you can kind of see why. Because right here it's saying that after 8 hours he is 0 miles from home, right? So anything beyond 8 hours is going to put him further from home in the opposite direction. So if I continued to draw this, at 10 hours he'd be down here because he'd be getting further from home once again. So it really wouldn't make sense to predict how far he would be after 10 hours unless it was to say that he would have passed his house and continue riding for 13.6 miles. The notes that you have continue on and talk about using using your calculator to find the line of best fit, and we will do that in class.